Welcome. Today the topic is inner sphere mechanism. Inner sphere mechanism and outer sphere mechanism. In this topic, what we will look that uh, details about of both inner sphere mechanisms and outer sphere mechanisms. And this topic is very important because in regards of the exam point of view. Okay, so to understand that inner sphere mechanisms and outer sphere mechanisms, we should have the concept of labile and inertness. Okay, because for labile and inertness, whenever you are studying inner sphere mechanism, this concept of labile and inertness will be used, although it is not used for outer sphere mechanism. But for inner sphere mechanism, the concept of labile and inertness is very important. And second, and it is the very important, that is the concept of high spin and low spin complexes. This is also very important. This is important both for inner sphere mechanism and outer sphere mechanism. Whenever we are making that coordination complexes, on that we have to understand that where it is high spin complexes, where it is low spin complexes. So that things I already discussed the details, that for labile inertness, okay, what look that electrons enters in Ag, then complexes are labiles. Means that we know that octahedral complexes, that is like this. This is Ag and this is T2G. So if electrons enters in the Ag orbitals, let's say we have that deep, then electron will, and this is high spin. 1, 2, 3, 4. So electron enters in the Ag orbitals, then this is labile compounds. Let's say you have that D for low spins, then electrons will come here. So no electrons enters in the Ag orbitals, then that are inerts. Okay, and that is except D8. Okay, D8 case, even the electrons enters in the Ag orbitals, but still that is inert. And another thing, that D1 and D2, these are always labiles, and that is explained by BBT. Okay, that is about of the concept of labile and inertness. And for the concept of high spin and low spin complexes, so we have to remember that spectrochemical series that I have discussed, and what you look that is the concept for it. If it is 45D series, then that are always low spin complexes, and if it is 3D series and oxidation state is plus 4 plus 5, then also always low spin complexes. Okay, and you look that only for that 3D series, 3D series, these are always low spin complexes. So we look only if it is 3D series and plus 2 and plus 3 oxidation states, then we will look that one concept is that 3D series. On that case, it may be low spin or maybe the high spin. Okay, so 3D series for low spin, if 3D series and plus 2, then what you look that in spectrochemical series, that is up to En, that is including En, all are high spin complexes. After En, the all are low spin complexes. Okay, so up to here high spin complexes, then low spin complexes will start. And if it is 3D series and plus 3 oxidation states, then up to water all are high spin complexes. After that low spin complexes, here that except each cobalt 3 plus. Okay, for cobalt 3 plus it is always cobalt 3 plus, because cobalt 3 plus always shows low spin complexes except like that halogen groups X minus, Cl minus, Br minus and N3 minus, that halogen type groups that I already discussed in the class. Okay, so this is the for high spin and low spin complex. We have to look this, that where this is high spin, where it low spin complexes will come, and this is used for, this is very very important concept while you are studying for that coordination chemistry. And labile and innoteness, we know that if electron synthesis in the s orbital, then this is labile, otherwise this is inert. Okay, so I give just a quick recap of labile and innoteness and high spin and low spin complexes. So now let's start with our main topic for today, that is inner sphere mechanisms and outer sphere mechanisms. Topic is inner sphere mechanism, that we can say that is ISM also, and outer sphere mechanism, that we can say OSM. Okay, so this inner sphere mechanism and outer sphere mechanism, this is a type of redox reactions. Actually inner sphere mechanism and outer sphere mechanisms is a one type of redox reactions where both oxidation and reductions will occur. Okay, so I can say that inner sphere mechanisms and outer sphere mechanisms is a type of redox reactions. So we know that redox reactions means where both oxidations and reductions will occur. Okay, and so redox reactions means that we have redox reactions are this and this is a type of redox reactions. So redox reactions, I mean that it may be inner sphere mechanism or it may be outer sphere mechanisms. Okay, so because this is a one type of redox reactions, so here what happened that a redox reaction means both oxidations and reductions will happen. Okay, so that is one is reductants, other is oxidant. So if we know the reductants means it is reducing others and itself it is oxidizing, so it reduce others and oxidize itself, that is reductants. And for oxidants, it oxidize others and reduce itself, that is oxidant. So this name is given that reductants and oxidants, that what it is doing with others. So if it is reductant means it is reducing others. Okay, so name is given that what its work to others, so it reduce others, that's why its name is reductants. Similarly this is oxidant, means it is oxidizing others, so it is oxidant. Okay, and if it is oxidizing others, then himself it is getting reduced, and it is reducing other himself, it is oxidizing itself. So let's say if we have the charge M2 plus, okay, so it is oxidize itself. Reductant means oxidize itself, so it means that from here to it is going to M3 plus. Similarly, in this case it is reducing itself. Let's say M3 plus, so it is reducing to M2 plus. Okay, so here we look that electron rich compared to this and this. Which is electron rich? This is electron rich, means that less charge means electron rich, and this is deficient, electron deficient compared to this. So now if anybody asks you then where the electron transfer will happen. Now this redox reactions means that what, where one side it is getting oxidation, other side is reducing reductions, means how it is happened by electron transfer. So electron transfer will happen from a reductant to oxidant or oxidant reductants. So since this is electron rich, and this is electron deficient, so electron transfer definitely will happen from electron rich to electron deficient, because which is rich that will only transfer, because here electron is present, so electron transfer definitely happen from here to here. So from here we note that electron transfer occur in redox reactions. Redox reactions I mean that may be inner sphere mechanisms or outer sphere mechanisms. Always occurs from reductants to oxidant. Okay. So this the electron transfer always occur from reductants to oxidant. So we just discussed about just the uh, interdictions of redox reactions. And the redox reaction, it may be inner sphere mechanism and outer sphere mechanisms. Okay, now we look that why we have that inner sphere mechanism and why we have that outer sphere mechanisms. So how you distinguish that whether it is inner sphere mechanism, whether it is outer sphere mechanisms. So for that, let's talk about some key points to distinguish between inner sphere mechanisms and outer sphere mechanism. So to distinguish inner sphere mechanisms and outer sphere mechanisms, let's say here we have that inner sphere mechanisms, that is, let's say ISM, and outer sphere mechanism, let's say this is OSM. Okay, now that what are the main difference between the inner sphere mechanism and outer sphere mechanisms? How will you say that by looking that it is inner sphere mechanism and it is outer sphere mechanism? So first and foremost point to distinguish inner sphere and outer sphere mechanism is that, so what you look here, that from inner, this word name it says inner. So from here we what is that, we guess that inner means that something that inner will happening, means inner we are looking something deep inner in this mechanism. So inner means whenever in the complexes, inner means we definitely say that the bond, like how the bond has formed. Okay, that things we will look. So here that from inner we can recognize that there may be some bond formations. So we look that bond. Okay, inner means we look, if you want to look that inner side of any complexes, then what we look that how the bond it is. Okay, how we can, whether it is easily able to break or not, that things we will look. So for inner, that what is happened, that bond formations and bond breaking will happen. Or sorry, so we can say that for inner. So we see that for redox reactions, what electron transfer we are doing. Okay, so since this is inner, means where some bond is there and we are looking something deeper for this type of mechanism. So what we say that electron transfer happen through bond. Okay, so that what we say, because redox reactions means that electron transfer will happen. Okay, so here electron transfer happen through bond, because you are here that inner sphere mechanism is inner bond is there. For outer sphere mechanisms, what we say that outer we look, it means that there is no bond in the complexes, means where electron transfer there will be no bond. Okay, so electron transfer not happen through bond, it happens through tunneling, that we will discuss detail while we are discussing on outer sphere mechanism. So here that electron transfer is not happen through bond, it happens through tunneling. Okay, here that electron happen through bond. Okay, so inner means that no bond, that things will be there. Outer means that bond will not come, we are doing some outer things. Okay, not coming to the inside of the complexes. So that is the first point. And secondly, what we see that here that electron transfer happening through bond means that electron transfer from one complex to another complex, you are doing the electron transfer. Means bond will form by how? By making the two electrons, one bond will form. Okay, so this is that bond. It means that two electrons are there, then we say that this is the bond between, let's say this is m bonds, let's say this is another bonds. So there between them they have the bond, means that while the two electrons they will form the bond. Okay, so the electron transfer is happening through the bond, means that bond is forming and bond breaking is happening here. So here bond formations and bond breaking occur, but here no bond form. Okay, so no bond form means no bond breaking, no bond formations, nothing that like things has happened for the outer sphere mechanisms. So if that bond formation, bond breaking is happening here, then what we say that here definitely a substitution reactions will occur, because we see that whenever there is a bond formation and bond breaking, so we are making one bonds and we are breaking another bonds, like this means this is a one type of substitution reactions. So it means that here substitution reactions occur. And for substitution reactions, what we have studied that, let's say you are breaking one bond and you are making another bond, means which bond you will make, which is reactive, that bond will break, and which is inert, that bond will not break. So that we explained by the concept of labile and inertness, because labile means that is reactive and inert means that is less reactive, so that will not break, and that labile which is reactive, that will break. So since here that substitution reactions has came, so here we will discuss concept of labile, that is reactive and inertness, that is less reactive. So here concept of labile and inertness will come, but here so no substitution reactions, no substitution reactions, so no concept of labile and inert, no concept of labile and inertness. Okay, Another points to distinguish between inner sphere and outer sphere. Here that whenever you look that for inner sphere mechanisms, the bridging ligands should be present. So bridging ligand must be present. If bridging ligands absent, then it never happened to inner sphere mechanisms. Okay, so that bridging ligands helps for this substitution reaction. So bridging ligand must be present, and if it is absent, then it will not happen through inner sphere mechanism. So it is easily distinguished that if bridging ligand is present and that is it is in oxidant, then this is definitely happen through inner sphere mechanisms. Another concept also need that both should be labile, that we'll discuss while we are discussing on inner sphere mechanism. So for distinguish between inner sphere mechanism and outer sphere mechanism, bridging ligand should be present for inner sphere mechanism, and for outer sphere mechanism, no bridging ligand needed. Okay, and another concept for inner sphere mechanisms. So these are the main way to distinguish between inner sphere mechanism and outer sphere mechanisms. So let's study one by one inner sphere mechanism and look the details about of that and discuss all that topic of inner sphere and outer sphere mechanisms. So these are the main points to distinguish between inner sphere mechanism and outer sphere mechanisms. And note that this is a one type of redox reactions where we have that reductants and oxidants, and this redox reactions means what? Redox reactions means that electron transfer will happen. Electron transfer must happen because one reductant and one is getting oxidant, means one is oxidizing, other is reducing. It means what? That electron transfer is happening. So redox reactions means that definitely will happen, that electron transfer. So electron transfer is happen, it means that uh, in the redox reaction. So this reactions may be inner sphere mechanism and outer sphere mechanism. It means that both the case of inner sphere mechanisms and outer sphere mechanism, that electron transfer is happened. Okay. So now let's go one by one. We'll discuss detail about inner sphere mechanisms, then we will go detail about the outer sphere mechanism. So first I am going to start with inner sphere mechanism. So this is also known as ISM. We can write shortcut. So for inner sphere mechanisms, what we see that here that bridging ligand must be present. So first and foremost point is that bridging ligands must be present. And that bridging ligand must be with oxidant. Okay, so bridging ligand must be present and that bridging ligand must be with oxidant. This is the first point. And second point, that here we say that at least we talk about of labile and inerts. Okay, so for inner sphere mechanisms, the the important points, that required conditions is at least one of the complex must be labile. At least one has to be labile for inner sphere mechanisms. If both are labiles, then also the reactions will happen. But if both are inerts, then the reactions is not happen through inner sphere mechanism. So at least one of the complexes must be labile. Okay. And third point, so if two labile, then reactions happen. But if all is not, then reactions not happen by inner sphere mechanisms. Okay, so this is the important points. First is the bridging ligand must be present, and second point is that at least one of the complex must be labile. So for inner sphere mechanisms, these points are these conditions must be satisfied. Condition must be satisfied. Okay, and third, yes, so the electron transfer will happen. Okay, so electron, since this is a reduction reaction, so electron transfer happen from reductants to labile. So reductants to oxidant. So this is the common point for both inner sphere mechanism or outer sphere mechanism, that electron transfer must be happen from reductants to oxidant. Okay, so now we will talk with the concept of labile inertness. Okay, so now we see that reductance means itself is getting oxidized. So we say that reductants are electron rich, and we say that oxidants are electron deficient, that we have seen. So electron rich, it means that this is little reactive, because electron this is what is it, that electron rich it has, so that reactions it will do. So this reductance is known as the labile, because the labile also reactive. Okay, so now we will say that reductant means labile, and oxidant means electron deficient, and that is inert. Okay, so now we will say that oxidant means inert, and this also you can remember by Rowley. It means that reductance is labile and oxidant is inert. Okay, this is the third point. And so electron transfer is always happens from reductants to oxidant. So now we will look that general mechanisms of inner sphere mechanisms, and we will look at examples, and we will look at factors affecting inner sphere mechanisms. Then after that we will go for outer sphere mechanisms. So the general mechanisms, general mechanism of inner sphere mechanism is, let's say we have that one compounds. So we generally take that two complexes. Let's say one complex is M L 5, and we have that any X, that halogen any bridging ligands. Okay, and we have another complexes, let's say metal M dash, and ligand let's say L dash, and this is 6. Okay, now what we will do that, so we will do that step 1, that is substitution reactions we will do, means that bond formations will happen. So substitution reactions we will do, it means that this bridging ligands helps in the bond breaking. So what will happen, this M L5, and this has the bond with X. Okay, so this X, again this M will make bond, so bond forming will happen here. So M dash L dash 6. Okay, so let's, it has the charge let's say it has the charge 2 plus, let's say it is also has the charge 2 plus. So if it is 2 plus, then only we remember that while we are doing the inverse pair mechanism, only look the charge of metal. So here the charge of metal is plus 3, okay, because this is x minus 1, let's say this 2, then x equal to plus 3. So charge of metal is plus 3 and charge of this is plus 2, because let's say L and L dash are neutral ligand. So if I are taking the neutral ligand, then charge will be 0. So this will be plus 3 charge and this is plus 2 charge. Okay. So this is oxidants, because this is electron deficient and this is reductants. Okay. So from here what you say, that electron transfer happen from reductants to oxidant, and in the oxidant what is there? That is uh, bridging ligand is there. So bridging ligands, we see that bridging ligands X, this is let's say bridging ligands, it should be it generally will be the halogen groups like Cl minus, Br minus, F minus, I minus, this type of compounds. And so we have discussed in that that is organometallics, that which are the ligands and which cannot be ligands. So they should have that octet should be completed, and they should first make that one bonds. After that, if have that extra bond, then they will make that bridging bonds. Okay, so that we have discussed. So bridging ligands can be this, and bridging ligands can't be water. Water cannot be bridging ligands, and NH3 cannot be a bridging ligand. So these are the bridging ligands. So that we already discussed in that organometallics. Okay. So this X can be either this and this. Okay, or any bridging ligands, that can be the X. So this will happen, that bridging ligands will make bond, the substitution reactions, it will help to make the bonds. Now what we'll do, step 2. So now that is electron transfer will happen. Electron transfer. So let's say that now we will look only the charge in the metal. Okay. So what is the charge here? Plus 3. And what is the charge here? That is plus 2. So just keep the charge of this to here plus 3 and charge of this to here plus 2. Okay. Now we will do that. Electron transfer will happen. So electron transfer is happen always from reductants to oxidant, because this is electron rich. Okay. So electron rich, because it is the less oxidations, means that is electron rich. So electron transfer happen from reductants to oxidants. So here electron transfer will happen. So this will become L5 M X M dash L dash 6. So electron transfer happened from here to here. So this get that plus 3 charge. Sorry, this get the plus 2 charge, and this get the plus 3 charge. Okay, after electron transfer. Now in the step 3, what will happen? That now we will look, we can go for 2, that is here also step 3, here also we have that step 3 dash. Okay, so 2 cases are possible. Now again what we look, that here we say how that first point is that here also oxidated reductants, and that we will look by, actually we will not first take oxidant reductants, we will take that whether it is labile and inert. So labile means that is reductants and oxidant means inert. So we will check that labile and inerts, okay, from these compounds. So if it is M3 plus and it is M2 plus, then we will check that whether it is labile or inert. So for inverse pair mechanism, at least one has to be labile. Okay, so first at this point, this is the first point. So here we will check that labile and inert, then at least one has to be labile. Then we will proceed this step 1. The forward process will happen. Okay, after that, so this I explained by reductant and oxidant, but that is always not right. Okay, so always correct concept is we will check that M and we will check that labile or anodes. Okay, so from that electron transfer will happen from labile to anode. Okay, so this concept of like charge, we cannot say this is reductant, this is labile. So we will look by taking that whether it is labile or anode, that metal. Okay, so that we will be clear while we are doing the examples. So what we will do here, that again you look that M2 plus and M3 plus. Okay, M2 plus and M3 plus, M2 plus and M3 plus. So here we will check that whether this metal with this complex is labile or anode. If both, if that at least one of this complex with metal 2 plus this complex, or this metal dash 3 plus this complex, at least one is labile, from here at least one labiles, then what happened, that ligand also transfer with ligand transfer happened. It means that here what we see, that ligand is with this, sorry, bridging ligand will happen. Okay, with bridging ligand transfer. Okay, so here that bridging ligand is with this complex. So now that if at least of this anyone is labile, then what happened, that this bridging ligand will transfer to here. Okay, previously here, now it transfer to here. So this will happen, that is we will look that N5. Okay, so just look the charge, not look anything about it, just look the charge. Ml, whatever the charge is, same charge we will put here, plus 2. Okay, and this is the ligand has, so bridging ligand has transfer. So this is M dash L dash. So see, whenever that substitution reaction happening, so whenever this X is making bond with this M dash, then what happened, that one L dash is removed. Okay, so this is not L6, this will become L5. This is L5, this is L5 is there. Okay, so now what happened, that this bridging ligand is transferred to here, so this is L5 and X is also come here. Okay, so whatever the charge, put the same charge here. Okay, so not look anything about of this, what will be the ligand has, bridging ligand has came, so charge is change or not. So don't look anything, whatever the charge is, same charge we will put here. Okay, now we look that what will be the overall charge. So since this ligand is neutral ligand, so this charge should be plus 2. Okay, since this is halogen, that is has the -1 charge, so this will be that 3, this is 3 minus 1, that is 2. So this overall charge will be plus 2. Okay, so first we will do whatever charge we will put, then according to the ligands we will take that what should be the overall charge. Now the step 4. Okay, so for step 4 what will happen, that we will do the solvent. Okay, so we will add the solvent additions will done. So what happened, that so wherever this halogens, that bridging ligands is there that no solvent substitutions will occur, only the substitution occur where here. Okay, so this will going to become M, and since this is we are talking about octahedral complexes, then this is going to become this all L5, all ligands will be exchanged with water, with that one water will be added, so that will become M H2O6 2 plus. Okay, so all L5 are replaced with water. With that, since these octahedral complexes, another water added, and complexes will become MH2O6 2 plus. Okay, and now for this there will be no water exchange will happen. So whatever the compound, same compounds will be right. Okay, so this will be no any water replacement will happen for wherever that halogens that bridging ligands come. So this will remain as it is. So this is going to be M L dash pi X, and the charge is +2. So this will be the final products, and this will be the final product if this is the final product if it is happening with the bridging ligand transfer. Okay, now for this case if that step 3 days, if both these complexes both are inert, okay, both are inert, then what will happen, that ligand transfer will not happen. So if at least one is labile, then ligand transfer will happen. After that electron transfer, if here both are inerts, then the totally mechanism will not happen. So here at least one has to be labile. For this case, after electron transfer, here that if both are inert, then the ligand transfer will. So we remember that for electron transfer, we are doing that two cases. We are looking at labile and inerts. First point is that here we look at labile and inert. Here at least one has to be labile. Then that substitution reaction will happen and electron transfer will happen. After that, after electron transfer, again we will look at labile and inerts. And if at least one is labile, then ligand transfer is also happen. And now in this case, if both are inerts, then bridging ligand transfer will not happen. If both are inerts, then no transfer of bridging ligands. Okay, so now this is happened without transfer of bridging ligands. So here the bridging ligand was there, so bridging ligands will be stay where it was previously. So the reactions will becomes ML5 X, whatever that is there, the same things will be here. Okay, so charge is whatever this, the charge will put here +2, and this M dash L dash 5. So whatever the charge, same charge we will put +3. Now we looked at what should be the overall charge. So this is +2 and this is -1. Okay, so this is +2 and -1, that is going to become +1 charge. So this overall charge will be +1. Okay, now this is the neutral ligands, because we will take that L and L dash a neutral ligand. This is going to be the +3 charge. So this is the complex. The next step is we will do solvent additions will happen. So what I say that wherever that halogens is there, that bridging ligand there will be no change will happen. So whatever the same things I will write, M L dash L dash 5 X +1, whatever +1, whatever that same things will there, wherever the bridging ligand there will be no replacement of water. Okay, now this here that not all ligands will be replaced with water, but one water will be added. Okay, so we note that for this case, without ligand transfer, wherever it happened, that here that water is replaced with all L5, that water is replaced. For this case, only water replacement will not happen, only one water will add. Okay, so this will be M dash, this L dash again come 5 and one water will added, because this is octahedral. Okay, so this is +3 charge. This will be the final product for this is the final product for if it is happening through without ligand transfer. So here note that whatever that L5, same L5 will be there, only one water is added, because this is octahedral complexes. But for this case, all ligand are replaced with water if it is happen with ligand transfer. Okay, so these things will look that these mechanisms will be very clear if you discuss with the examples. So let's take that examples for both case, like if it's happening with ligands and electron transfer, and one is with electron transfer but ligand transfer is not happening. So both the examples we will look to clear that these mechanisms. So first examples we have, that is examples like let's say we have that CO NH3 Cl 2 plus is there, another is Cr NH3 6 2 plus. Okay, so what we see that for Enos pair mechanism, one and foremost is first is the bridging ligands should be present, and bridging ligands should be with the oxidants, and at least one has to be the labile, and oxidant and reductants is actually checked by that metals whether it is labile and inerts. So we know that how to check the labile and inerts. Okay, so don't put that this is this concept also right, but the maximum correct is that look whether labile or inerts. From labile and inerts we will decide that whether it is oxidant and reductants, not do that first oxidant and reductants and say this is labile and inert. Okay, so first we will look that labile and inerts, then according to that we will give that whether it is oxidant and reductants, because only so we say that reductants is always labile and oxidant is always inert. Okay, so first we will look that labile and inerts. So foremost thing is that one has to be labiles and the bridging ligands should be there. So here bridging ligands is there. Okay, so now we look that labile. So first thing is that labile. So for this, what you say that this is cobalt. Okay, so first we will take the oxidation state. So this is x minus 1, this is equal to plus 2, so x is equal to plus 3. So this is in plus 3 oxidation state, and this is since this is neutral ligand, so this is plus 2 oxidation state. Okay, so now this is cobalt 3 plus and this is chromium 2 plus. Okay, so this cobalt 3 plus means that is D6, and if it is cobalt 3 plus, all are strong field ligands, because we see that if it is 3D series with plus 3 oxidation state and it is cobalt, then all are strong field ligands except that halogen groups and some like N3 minus and H2 minus and SCN minus. Except this, all are strong field ligands. So this is ammonia, this is also strong field ligand, means low spin complexes. It means that I will like this way. So the electrons will be so low spin, so 1 2 3 4 5 and 6. Okay, so for now for this case, what that this is chromium 2 plus, that is D4. So this will be, and electrons are, so since we say that any 3D series, if it is plus 2 oxidation states, then up to En all are weak field ligands. So NH3, then En, so these are before En is coming, so this is weak field ligands. So this is high spin will occur because this is weak field ligands. So electrons will be 1 2 3 and 4. So you know this is Eg and this is T2G, this is Eg and this is T2G. Now that if what we say that for labile inerts, what we say that except D8 and D1 and D2. Okay, so this is D8, this is that is exceptional, and D2, D1 and D2, that is DBT. These are labile. So except this, any electrons if enters in the Eg orbitals, then that is labile, and if it is not entering in the Eg orbitals, then that is inert. So this is inert and this is labile. So from here we understand that this is labile. So labile is reductants and inert means oxidant. Okay, so from this what you say that this is labile compounds and this is inert compounds. This is labile, that is this is reductants, and this is inert, and that is oxidant. Okay, so one thing on that is at least one has to be labile. So one we get, that is labile, and that bridging ligand should be with the oxidant. Okay, so bridging ligand is with oxidant, so both the conditions are satisfied. Now we will do that inverse pair mechanism. So if both the conditions, first condition is bridging ligand should be present, okay, bridging ligand, and second condition is at least one has to be labile, so one is labile, and bridging ligand also there, and bridging ligand should be with the oxidant, so bridging ligand is with oxidant, so both the conditions are satisfied. Now we will do that inverse pair mechanisms. Okay, so before doing inverse pair mechanism, check that at least one is labile or not. Okay, if it both are inerts, then it will not happen through inverse pair mechanisms. Okay, and that bridging ligand is present or not. So if bridging ligand is present, then it will at least one of the complexes bridging ligand should be there, and bridging ligand should be with the oxidant. So these conditions are satisfied, then only we will do that inverse pair mechanisms. Okay, if bridging ligand is not there in the both the complexes, then it will not happen through inverse pair mechanism. So now we will do that inverse pair mechanism. So first is substitution reactions. Substitution reactions will happen, that is NH3 pi CO Cl, then here chromium NH3 6, this will happen, that first is substitution reactions. This is a step 1. Okay, so whatever the charge, this is +3 charge, so put here +3 charge, this is +2 charge, so put here +2 charge. Now what we will do after substitution reactions, there will happen electron transfer. Step 2 is electron transfer will happen. Okay, so electron transfer is from always reductants to oxidant, so from labile to inerts, so from here to here electron transfer will happen, so that complexes will become, and again NH3 pi COCl Cr H2O. So see that whenever that transfer happen, one H2O will be released, so one NH3, whatever the ligand, one NH3 will be released, so this will become 5-3, because code we are talking about octahedral complexes, so 6 ligands will be there. Okay, so 5 plus 1 6, this will be that NH3 pi cobalt, then we have that Cl, we have that chromium H2O pi. Okay, so this is charge with electron transfer will happen, so this is going to be +2 and this is going to be +3 charge. Okay, so now again we will look that labile and inerts. So this is cobalt 2 plus and this is chromium 3 plus. So now this cobalt 2 plus means this is D7 and chromium 3 plus means it is D3. Okay, so if it's D7, then what is okay, so this is D7 and it is with ammonia. Okay, so we said that for 3D series and it is with +2 oxidation state, all the transition metal complexes. Okay, so what is it, up to En all are weak paired ligands. So this is ammonia, so this is also weak paired ligands. Okay, the cobalt exceptional is for 3D series. For plus 2 series all are weak paired ligands up to En. So this will be weak paired ligand. So this is 1 2 3 4 5 6 7, and this is 3, so this will be 1 2 3, because chromium 3 plus, that is D3. So for D3 case, high spin low spin complexes will be that is not applicable. So this is Eg and this is T2G, Eg and T2G. So electrons enters in the Eg orbital, so this is labile, and this is not enters, then this is inert. Okay, so we get that what is that at least one has to be labile after electron transfer. So if one is labile, then it will go through with bridging ligand transfer. Okay, so this is labile and this is inert. So if one is labile, then it will go through with the ligand transfer. So step 3, with ligand transfer, okay, or with bridging ligand transfer. So what will happen, that this previously Cl was with bridging ligand is here, now it will transfer to here. Okay, so this is transferred to here. Then the complexes will be CO NH3 5, another complexes will become Cr H2O5, and this bridging ligands will come. So what will the charge, whatever the charge put here, this is +2 and this is +3. Okay, now we will look at what will be the overall charge. So this is neutral ligand, so this is +2, and this is, since this is has that -1 charge, so 3 minus 1, that is 22, so charge will going to be +2. Okay, now we will do that solvent. So what we will do, that whenever the bridging ligand is happening, okay, for that case, here in this case all that NH3 is replaced with water, so that will going to become CO H2O. Since this is octaedral, then this is going to plus, and wherever the bridging ligand will there, no water replacement will happen on that case, so this is going to be Cr H2O5 Cl 2 plus. So this is the final product. Okay, likewise we can solve. So let's take the another examples where that ligand transfer will not happen. So another examples, like if we have rubidium NH3 5 Cl 2 plus, another is chromium H2O 6 2 plus. So another examples, let's look that for this case. Now what we look that always before doing inner pair mechanisms, what you look that whether it will happen to inner pair mechanism or not. First point to distinguish the bridging ligand is there or not. So bridging ligand is present, so it had the chances to do inner pair mechanism. Now we will do that whether labile or inert. So at least one has to be labile, and then only inner pair mechanism will happen. So here we look that this is x -1, that is +2, so x is equal to +3 charge. This is +3 charge and this is +2 charge. Okay, so this is with rubidium 3 plus. So this is for this series, because this is with iron series, iron group. So iron groups, so this is having that 4s2 3d6, so it is have that this is, so this is 5s2 for d6, so it will have that group like d5 because +3 oxidation states, and this is had chromium 2 plus, that is having that d4. okay, so whenever this is 4d series, 5d series, always low spin complexes. So now this will going to becomes this, and so here d5, so 1 2 3, so this is the low spins always because 4d and 5d, so 1 2 3 4 5. So 1 2 3 4 and 5. okay, so for this case d4, this is eg and this is t2g, this is eg, this is t2g. so d4, so 1 2 3, this is high spins because for +2 3d series up to en all are weak pair ligands, so this is 1 2 3 4. so electrons enters in the ag orbitals, means this is labile and this is inert. okay, so at least one has to be labile for inner pair mechanism, so one is labile, so we will go through inner pair mechanisms. so both the conditions are satisfied, one bridging ligands is there and that is also with oxidants, and at least one has to be labile, this is also satisfied, so we will go through inner pair mechanism. so this is inert and this is labile, so we will go through inner pair mechanism. so step 1 is substitution reactions. okay, so for the substitution reactions, what happened that one water will be released because one halogen is doing, so substitution is what bond is making and bond is forming, so this is make bonds and one is release, so this is become R NH3 5 Ru, then this is Cl, then this is chromium H2O 5. so whatever the charge put here, this is +3, this is +2, so not look for charge, so whatever the charge, same charge will be put, so do not more intentions on charge, so whatever the charge here, the same charge will put. okay, so now that step 2 is electron transfer. so from electron transfer is from labile to inert, so this is labile, so here to here electron transfer will happen, so that is going to be NH3 5 okay, so this is becomes, now this is become +3 and this is become +2. okay, now we will do again, this is rubidium 3 plus, sorry, so electron transfer happened this here to here, so this is going to be +2 and this is going to be +3. so now we will do that again, we will look that labile and inert for ligand transfer. okay, so this is for whether this is happened through inner pair mechanism or not. For that case we will check labile and inert, after that we will do that electron transfer. now again we are checking that labile and inert to do the ligand transfer. okay, so now this is rubidium 2 plus and this is chromium 3 plus. so this rubidium 2 plus means that is d6 and this is d3. okay, so this is d6 and this is 4d series. so 4d series, this is always low spin. so here that what will happen, so 1 2 3 4 5 and 6, because this is always low spin, this is Ag, this is T2G, this is Ag and this is T2G. so electron d3, so 1 2 3, so here what we see that no electron is entering in the Ag orbitals, so this is inert, this is also inert. So if both are inots, then what we will do, that ligand transfer will not happen. So this is also inert, this is also inert. Okay, now note that if here both are inert, then total that inert pair mechanism will not happen, but here that both are inert, then ligand transfer, here that you are checking level inert to do the ligand transfer, here both are can be inert, but here can't be inert. Okay, so now if it is both are inerts, then step 3, that is I will do that without bridging ligand transfer. Bridging ligand transfer will happen. So that is wherever that bridging ligand is previously, the same it will stay. So this is wherever the bridging ligand here it was, so bridging ligand will be there itself. So that reactions will becomes NH3 5 rhodium Cl, or and this is here. So one water allergy we that I removed, so this will become 5. Okay, so whatever the charge, this is +2 charge, so put +2, and this is +3 charge, put +3. Okay, so now this is +2, so this is 2, this is -1, so this is overall going to be charge +1. So charge is +1, and this is +3 charge, so here also +3 charge, because this is neutral ligands. Okay, now we will do that solvent. So you see that wherever that bridging ligand is there, there is no solvent replacement, so whatever the complex, write as it is. This is +1, and here that one water will add it. No, this whatever the ligand will not replace, so here same water, so it will going to be CrH2O 6 3 plus. So this is the final product. Okay, so you see that where ligand transfer will happen, where ligand transfer is not happen. So now that here that RTS for this case, rate determining steps is step 3, not step 3. Why? Because here that without bridging ligand happened, and that rate determining step is step 3. And for this case where that ligand transfer has happened, that is bridging ligand transfer happened here, rate determining step is step 2, not step 3, that is step 2. Okay, so this you have to be remember. So this is the mechanisms, general mechanisms, and this is that where that how we will do the with examples. Okay, now we will look that the factors affecting rate of inner sphere mechanisms. Factors affecting rate of inner sphere mechanism. Okay, so what are the factors that affect the inner sphere mechanism? So here mainly the factor is bridging ligands. Okay, so how the bridging ligands, type of bridging ligands, it depends, that nature of bridging ligands. Okay, so first point is size of bridging ligands. So that size is high, then rate is also, rate of inner sphere mechanism is also high. Okay, so like if we have that I minus bridging ligand is there, then the rate is high, then Br minus then Cl minus, then F minus. This is the first factor on rate, that is size of the bridging ligands. Second is electronegativity of bridging ligands. Is indirectly proportional to rate of inner sphere mechanisms. So if that bridging ligands, electronegative of bridging ligand is more, then that rate will be decreases. Let's say if we have that OH minus is a bridging ligand and we have that F minus is a bridging ligand, then the rate will be high with this, because electronegativity will be this, so bridging rate will be this, that is inversely proportional to bridging ligands, electronegativity of bridging ligands. And third factor is that if the if conjugations in bridging ligands increases, then rate also increases. So these are the some factors where the rate of inner sphere mechanisms depends. Okay, so after discussing up to this inner sphere mechanisms, let's go with outer sphere mechanisms. Now we'll look on the next type, that is outer sphere mechanism. Outer sphere mechanism. Okay, so for outer sphere mechanisms, what we say that there is no bond formations will happen, and it high electron transfer, electron, so obviously that it is a redox reactions, means that electron transfer, this is a redox reactions, inner sphere mechanism. About outer sphere mechanism, it is a redox reactions. Redox reaction means electron transfer is definitely happened. Okay, so electron transfer is happened, means that so here outer sphere mechanism, no bond is formed, so electron transfer must be happen. So for electron transfer, it will happen through tunneling. Okay, here no bond form and no bond break. It means no substitution reactions. So no substitution reactions means no concept of labile and inots. So here we will not look about of labile and inert. So we will not discuss about of labile and inertness. So we will directly look that from the complexes whether it is reductants or whether it is oxidants. Okay. So here that electron transfer will happen. Electron transfer happen through tunneling. Okay, so here also we will look that some examples. We will do. I will look the general mechanisms and we will solve that examples, and I will look that factors affecting the rate of outer sphere mechanisms. So first thing is so let's say we have that complexes is given. Let's say P H2O6 2 plus, and let's say P H2O6 3 plus is given. Okay, this complex is given. Then I will look that reductants and oxidants. So here we will not use the labile and inert, that concept is not used. So I will look that this is +2 charge and this is +3 charge. So this is with +2 and this is with +3. Okay, and remember that here no bridging ligands bridging ligands not needed, because it is happened through without bond forming. So bridging ligand is needed for bond making and bond forming. So here bond concept is not there, so we not need any bridging ligand. So now bridging ligand is there. So now we will look what let's say here this is that in this. So we say that wherever this is high charge, so this is means electron deficient, so this is oxidant, and this is low charge means this is electron rich, that is reductants. Okay, so electron transfer is always happen from oxidant to reductants, electron transfer. Okay, now here since we are not have the Laval enough concept, so we will look directly with the reductants and oxidants. From that we will solve it. Okay, so electron transfer always happen for redox reaction from reductants to oxidant. Okay, so then now we will look the general mechanisms. So what the mechanism says. What the mechanism says that here we see the reductants. So let's say I am taking the shortcut reductants rate, and this is oxidant. So let's say I am taking that oxidant. Then what will do that if that reactions will happen, then what will do that this will becomes H2O6. This is electron transfer happen, then this is 3 plus, and this is going to be H2O6. This is 2 plus. Okay, so now that I'm doing that mechanisms. So these mechanisms happen through tunneling. So how the mechanisms will be look like. So we look at general mechanisms. So let's say I'm taking this is reductants, and let's say this is oxidant. Okay, so now that step 1 is that here the precursor complexes will form. Okay, so precursor complex form. Okay, so precursor complex, so that is we see that are reductants and oxidant. Okay, so they will come closer, that is precursor. Then what will do that step 2, and that it will go to the excited state. Excited state that I am representing by this. So it will go to excited state, that is say R and O. So this is go to the excited state. Okay, now in the step 3, so after going to the excited state, now that electron transfer will happen. Okay, so now the electron transfer happens. So electron transfer is from reductants to oxidant. Okay, so reductants means it's reduced other, and itself it is oxidize. So if it is R, then it is going to be that R plus, that is oxidations. And if it is oxidation, it is doing oxidations to other, it means it is reduce itself. So this is, let's say O, then it is going to be O minus. So that's what it says, that this is getting electron transfer, that is from reductants to oxidant. So this is one electron it is transferring, so it is getting that R plus it will become, because it is transferring, it is releasing one electron. So if it is release one electron, then it get that positive charge. So this is going to be that R plus, because it is releasing electrons. So electron transfer is happened from reductants to oxidant. Okay, so this get R plus because it release one electrons, and this get it accept one electron, so this get O negative. Yeah, and it is still in the excited state. So at the excited state, this electron transfer is happened. After that, what happened then? Step 4, then it will come to that de-excitations will happen, means that excited state there, it will come to the ground state, de-excitations, that is R dash O minus. Okay, so this is represented excited state, so this is removed because it comes to the ground state. Now after that this will become the R plus one compound and O minus another compound. Okay, so this is the compounds will form. Okay, so firstly this was the compounds. Now after electron transfer this will happen. Electron transfer is happened at the excited state. So why that electron transfer is happened at the excited state? Why not at the ground state? Okay, so whenever we see that if we have the complexes, any complexes, let's say M, so any metal M, let's say it has the charge Mn, and another metal is, let's say, N, and it has the charge M. Okay, so if this is the metals, or we can say, let's say, any metal, let's say +2, and metal is +3 charge. Okay, so whenever the charge is low, so you see that for these complexes that its size is, if it is size is like this, and if it is +3 charge, then you see that in this case this is the metal get contracted, means high size means it's contracted, means it is something like this. Okay, so this is something like this. So in this state whether electron transfer is happened, because you see that this is this types. So here that electron transfer is, since the bond length and this bond length are not different, so whenever this compound close to here come close to here, then this is something like this. So here that here is something like this, so no electron transfer will happen. So here we are not making the bond, we are making the electron transfer from the tunneling, like, so if they have that like comparable size, then only electron transfer will happen. So for that case, if it is excited state, if you take them in the excited state, then what happened that contractions will happen, contractions in size at excited state. It means that it has the charge, so this is something, this is, so this size also decreases. Let's say this will become like this, and it is also become the comparable size. Okay, so now the size is at comparable at the excited state. Now that electron transfer will happen with this, because they have the comparable bond length. Okay, so at excited state, contraction size at excited state or bond length of the metal are comparable. So then that electron transfer will happen. Okay, so that's why we are doing that excited state electron transfer we are doing. Okay, so since here no bond forming is happening, so this is the general mechanisms that will do whenever we are doing that outer sphere mechanisms. So what we say that if that bond length is comparable, if the bond length is nearly same, then that rate of outer sphere mechanism is fast, and if that bond length is different for the two complexes, then the outer sphere mechanism will be slow. Let's say it has the bond length, let's say it has a 0.05 Armstrong, and it has the bond length, let's say 0.0499. Then another complex is, let's say 0.2, another is 0.03. so in this case here that outer sphere mechanism is high. For this case, this is the this will become the fast and this will become the slow. So because this is the comparable bond length, this is 0.01 difference, so 0.001 difference, here that 0.01 difference. So this difference is very less than that outer sphere mechanism is fast. Okay, so in this way, that for outer sphere mechanism, that reactions is proceed. First it will go to the excited precursor complex will form. After that it will go to the excited state. At excited state, that bond length of both the complexes become comparable, means that size will be, they adjusted it, and after that electron transfer will happen. Okay, so now we'll look some examples, and we'll study that what are the factors that affect that rate of outer sphere mechanisms. Let's we have that, if we have the examples like let's take the same example. FeH2O 6 2 plus is there, and we have that FeH2O 6 3 plus. So here we need the concept of high spin and low spin complex, so that is always important. So high spin and low spin complexes, then we could easily do that outer sphere mechanism, because here we know it Lavalent Enot concept. So this is Fe2 plus and this is Fe3 plus. Okay, so this is Fe2 plus, means this is D6 and it is have the D5. So whatever I said that for 3D series and it is with +2 oxidation states, then still En or R high spin complexes, means all are weak field ligands. So this is also high spin. Okay, and for +3 oxidation state up to water, means including water, all are weak field ligands. So this is again high spin complex. So make the bonds. Okay, so if I took that, then D6 high spin. So 1 2 3 4 5 6. This is also D5. So 1 2 3 4 and 5. Okay, so now that how the electron transfer will happen. So here we will not discuss about a Lavalent Enot concept. Okay, so how the electron transfer will happen. So first it will go to the excited state at the comparable size, then the electron transfer will happen. So this is Eg, this is T2G, this is Ag, and this is T2G. So electron transfer is always happened from labile to Enot. So since this is +3, so this is Enot and this is labile. Okay, so from labile to Enot, so from here to here the transfer will happen. So always remember that electron transfer for reduction reactions is always, so not labile. This is here labile and Enot concept is not there. So this is what you say, this is reductants and this is oxidant. This is reductants and this is oxidant. Okay, so electron transfer is always happen from reductants to oxidants in redox reaction. So from here to here electron transfer will happen. So here for this case, here also vacancy is there because 2 electrons can be filled. Okay, so that the past chance is, this is Eg is strong bonds and this is weaker. So this is generally pi bonds like this. This is generally sigma bonds and this is generally pi bonds or non-bonding. So if there any vacancy is there, any like if that half filled is there, so chance is there for T2G, then first we will do T2G, then we go for Eg. So electron transfer is happened from this to this, that is from T2G to T2G. So if the chance is with T2G, then first we will do the T2G, because this is the weak bond. So this is easily, so this is weak attraction, so this is easily break. Okay, so that is T2G to T2G. And next we will look another examples. So this will happen and it will do that electron transfer will happen. So this is going to be after that transfer, this is going to become D6 and it is going to become D5. So D6 means there is going to become Ap2 plus, and this is going to becomes Ap3 plus. So Ap3 plus means this, the electrons H transport from here to here, so this is going to become that Fe H2O6 3 plus, and this is going to become Fe 6 2 plus. So here we will note that the mechanisms, like in the spare mechanism we have to do first Label inert, then we will do electron transfer, then we will do again Label inert. That thing we will not do, directly we will do that electron transfer. So electron transfer is done, so the exchange it, then this is the final product. Okay, so outer spare mechanism is little bit easy compared to inner spare mechanism, so we will only check this and do the electron transfer. Okay, now we will look at another examples. Let's say if we have the examples, let's say we have that CrH2O, CrNH3 6 2 plus, and let's say CrNH3 6 3 plus is there. Okay, so for this case, so here no bridging ligands, so that things we will do for outer sphere mechanisms. So we just do that reductants and oxidants. So this is +2 chromium 2 plus, this is chromium 3 plus. So this is low oxidation state, means this is reductants and this is oxidant. Okay, so electron transfer happen from reductants to oxidations. Okay, so how the electron transfer happen, that we will do, draw that Cr2 plus. Cr2 plus means this is D4, and Cr3 plus, it means it is D3. Okay, so for this is ammonia. So for +2 oxidation state till En, all are weak field ligands. So this is again happen through high spin complexes, and this is also so here high spin low spin complexes will, that is not applicable, so I will do that. Okay, so this is Ag, this is T2G, this is Ag, this is T2G. So electrons will be depot. So 1 2 3 4, here 3, so 1 2 3. Okay, so now that here what you see that here that vacancy is there. Okay, so here that vacancy is there, but we see that this is half filled. Okay, this is half filled. So if this is half filled or full filled, they are generally stable. So now we will not do by T2G to T2G, we will go for Ag to Ag. So now we first we look at where is this is reductance, so reductance to oxidant, so transfer will happen from here to here. Okay, so transfer is always from reductance to oxidant. So electron transfer here it will happen. So after electron transfer, what will happen? Electron transfer you did, and what will happen? This will becomes okay. So this is going to be, this is Ag and this is T2G, this is Ag and this is T2G, and that is going to be 1 2 3. This is become 1 2 3 this. So this is the happen after we do the electron transfer. So not that electron transfer part is going to the precursor, then it will form the accelerated state, then only the electron transfer will be happen. Okay, so it will happen from Ag to Ag. So here T2G to T2G. And if we take that other examples, we will talk more examples, so that let's say we have the examples, like if we have that B phenyl group is there. Okay, this is, or or let's say any pi acceptor ligands is there. Okay, 2 plus, another is ApCO6 3 plus. So what you see that if it is pi acceptor ligands, and then we say that whenever the pi acceptor ligands, then that is always for that case strong pair ligands will be it is the strong pair ligands. So pi acceptor is always strong pair ligands, whatever that metal is, whether it is +2 or whether it is +3 charge. Okay, so this is going to be that Ap2 plus, and it's going to be that Ap3 plus. So this is D6 and it is D5. So since this is strong pair ligands, okay, so this is low spin complexes, this is also low spin complexes. It means this type of compound. So this is D6, so 1 2 3 4 5 6, this is 1 2 3 4 and 5. So this is Ag, this is T2G, this is Ag, and this is T2G. So electron transfer is always from oxidant to reductants. This is +2 charge, this is +3 charge. So +2 charge, low charge means reductants, and this is oxidant. So transfer is always from reductants to oxidants. So this will get transfer from here to here. So after electron transfer, this is reductants, this is oxidants. Okay, so after electron transfer, what we'll do, make that compound. So this is going to be the Ag, and this is T2G, this is Ag, and this is T2G. So this is going to be 1 2 3 4 5, and this is going to be 1 2 3 4 5. So this electron has came, so this becomes 6. Okay, so the electron transfer is from T2G to T2G, and here that ligand is pi acceptor ligands. Here that T2G to T2G, here also T2G to T2G, but ligand is not pi acceptor. Okay, water is not a pi acceptor. Okay, water is not pi acceptor ligands. This is the case. So we have discussed T2G, Ag, and another examples, like if you take that CONH3 6 2 plus, and if you take CONH3 6 3 plus for this case. Okay, so for this case, if you look here, then this is cobalt 3 plus, and this is, so this is cobalt 2 plus, this is cobalt 3 plus. So what I say that for 3D series or +2 oxidation state, all the metals, okay, up to En, all are weak paired ligands, including En, all are weak paired ligands. So this is weak paired ligands. So this is D7, and it is happen that is high spin, and this is D3. So this is going to be the D6, and for cobalt 3 plus, okay, for transition metal complexes, if it is +3 oxidation states, then up to water, all are weak paired ligands except what we say that cobalt 3 plus. So cobalt 3 plus is, for that case, all are strong paired ligands except halogens and that N3 and SCN minus and that S2 minus, all are strong paired ligands. So this ammonia, this is also strong paired ligand. So this is after transfer complexes. So if you do the electron fill, okay, so fill the electrons. This is Ag, and this is T2G, this is Ag, and this is T2G. So electrons are, that says 1 2 3 4 5 6 7. So electrons are 6. So 1 2 3 4 5 and 6. Okay, so now this is high spins, and this is low spin complexes. So electron is transfer always happen from reductants to oxidants. Okay, so this is the reductants and this is the oxidant. Okay, so now that electron transfer is from if the chance is here, then always from here to here, but here all are filled. Okay, so whether it is half filled or full filled, then electron transfer will not happen. So not that fully half filled, here no vacancy, fully half filled or fully filled, then electron transfer not happen to that cell, to that T2G or EG. Okay, so here TTG, that is fully filled, so here not will happen. So I will do transfer to EG. So electron transfer, what I will do that this transfer to here, so that will become okay. So this is AG and this is T2G, this is AG and this is T2G. So electron transfer is happened from here to here, so that means that this is 1 and 2, this is from 1, this is release. So 1 is transferred to here. So this after electron transfer, this complex will form like this. Okay, now it will become that 1 2 3 4 become D6 and it will become D7. So what things we did here, that for this case what things happen, that electron transfer from T2G to EG, because electron transfer is always happen from reductants to oxidant. Okay, so not from here to here, because reductants to oxidant electron transfer happen. So I do the transfer. So what things we did, that here T2G to EG electron has transfer. So T2G to EG. So it is high spin, another is low spin complexes. So what that are red, whenever you talk about this case and another things, look, if CO NH3 6 2 plus and CO NH3 6 3 plus, this case, or the possible is the same things will happen En also up to En. This is weak field ligands 6 2 plus and CO En 6 3 plus, this case, or CO water also 6 2 plus and CO that is 3 plus. So all this case, this the same things will happen if we can check it. So all this case same things, that is one is high spin, one is low spin will be there. So let's say this is this will be that high spin, then this is going to be low spin, this is high spin, then this is low spins, this is high spin, then this is low spins, and this is high spin, then this is low spins, and the electron transfer will happen both or the case T2G to EG. Okay, in this case. So in this case what happened, that first we will do while we see that mechanisms of outer sphere mechanism, first it will go to that excited states. After that excited state, bond length will come into a comparable size, then the electron transfer will happen. But for this case, first that it will go to excited state and bond length will happen. That always that is happen for all the cases. With additions to that, here that spin also get changed. Okay, so the spin will come into the same spin, that is it comes to, let's say, a low spin to low spin, both will become low spin at the excited state. So here that both things will happen. First is it will go to excited state and bond length is going comes to into comparable size. With addition that spin also changing is happen. Okay, so for this electron transport, both has to be in the one spin with the same spin. So here's changing in the spin also needed. Okay, so note that for outer sphere mechanisms, what happened that the bond length should have comparable size. Okay, and second point that both complex should have same spin. Okay, so this both things will happen, then only that electron transport happen. Outer sphere mechanism to do electron transport. Okay, this both the things will happen. So here that both things we have to do. First we will do that bond length will take into a comparable size. With that we have to change the spin on also. Okay, so for this case we see that both are this is also high spin, this is also high spin, so here no need to change the spin. Okay, so for this case also we see that both are low spins. If both are low spins, then we no need to change the spin, only we need to change the size of the bond lengths. Okay, here also you see that this is high spins and this is also high spins. Okay, because here high spin low spin concept is not applied, so let's take this is high spins, though here also spin no need to change, only you need to change the bond lengths. Okay, here also both are high spin. So we see that for outer sphere mechanisms, two things are needed. First, that is bond length will come into a comparable size. That is happen at the excited state. At the same times, at the excited state, both will be come into that same spin. If it is already in the same spin, then that rate will be high. If it is in the different spin, then it need to change into the same spin to do the electron transport. Means that spin change is also happened at the excited state for that case. So if the spin are different, then rate will be decreases. Okay, so that factors affecting rate of outer sphere mechanisms are first is that the bond length should be at the comparable size. If they have, then that is that first factor is that that is the experimental value, that if they give it, then we can distinguish either this is not as general. So bond length should have comparable size. Okay, and next thing is that both have same spin. That is, so if it is high spin and high spin, then this will be the rate will be high, the high spin and low spin case. Okay, and third things is that if electron is transferring from T2G to EG, that case here, that what you say that this is generally pi bonds or this is generally non-bonding. So we see that for octahedral cases, these are generally form the sigma bond, this generally form the pi bond. So if that bond is happening, electron is transferring from this pi bonds or non-bonding, then that rate is a little bit high compared to sigma bond, because sigma bond is a little bit strong, so to break we need some energy. So if that electron transfer is happening from this T2G to T2G, then that rate will be high. Okay, so that will be T2G to T2G will be the rate is high. Okay, so T2G, so I can write rate is, if it is T2G to T2G, and if T2G if we have that pi acceptor ligands, then rate will be very high, because that electron will transfer from metals to ligands, then ligand to metal. Okay, so in between two metals ligands will come, so which facilitate to pass transfer of electron. So if pi acceptor ligand is there, that accept that ligands from metals and it transfer to another metals. So if ligand like pi acceptor ligands are there, then the rate will be very high. Okay, so in this case, so we have the case like this is the pi acceptor ligands. So for this case, what happened, that this pi acceptor ligand accept the electrons from metals and it will transfer into the another metals. So in between two metals, pi acceptors act as a intermediate, so that transfer will be very speed, because when the electron transfer from metal to metal, then there will be some like that we say that comparable size, it has two comps and that things will be there, so that will become a little bit time taking for to electron transfer. But if it has that pi acceptor ligands, so that will be easily do that, it accept electrons from these metals and it will give to another metal, so that case electron transfer is very high. So if two metals and if have a pi acceptor ligands, then that is very high speed. Okay, so T2G and if have that pi acceptor ligands, then that rate is high. Then we will have that T2G to T2G, where that pi acceptor ligand is not there, that case. Then we have that concept of EG to EG. Okay, then we have that T2G to EG. So because here we are changing. Okay, so the same things will be transferred is high. So T2G to T2G, T2G to T2G, and EG to EG, then T2G to EG. Okay, after EG, T2G to EG, and so see this case EG to EG, and this T2G to EG case, this is like if we have that one is high spin and another is low spin complexes. Okay, so these are the generally T2G to EG, so the spin is different on that case. This the rate is very low. Okay, so here that rate is low. So this is the what that rate depends on how that outer sphere mechanisms depends on these factors. So we will do the examples to clear more on these points. Okay, and note that if another case, let's say that rate is something like T2G to T2G, and it is 4D or 5D series, and we have that pi acceptor, then that is very high rate. Okay, so first we will look that if 4D 5D series, then that is very high, then pi acceptor, here also pi acceptor is there, on that case this rate is very high. So these are the rates. So we will solve the examples to clear on this point. Let we have the examples like example is B. Let's say we have that 3 6, let's say 2 plus and 3 plus is there. Another let's say A, P each, chromium H2O 6, 2 plus and 3 plus is there, and let's say FeNH3 6 2 plus and 3 plus is there, and let's say D we have that cobalt NH3 6 2 plus and 3 plus is there, and we have that E, that is rubidium, let's say CN6 2 plus and 3 plus is there. So calculate the rate of R2 spare mechanism. So how the rate will be? So for this case we see that here that what you see here, that pi acceptor ligands, but this is 3D series, this is also pi acceptor ligands, and this is that same series, and that part that is 4D series and 5D series. Okay, and this case, so if you calculate all this, then we see that first will be the rate case. We look that this case, what will say that rubidium 2 plus and rubidium 3 plus will be there. Okay, so this case this is for this series, and this happened through that T2G to T2G. So you see that here so this is D6, so 1 2 3 4 5 6, and this is D5 1 2 4 5. So this, and with pi acceptor ligands, and it is T2G to T2G. So this is T2G, first will be that E. Okay, because here this is T2G to T2G, pi acceptor ligands is there with that 4D series. Then we'll have that this A, the same things will be the same case. This A case, how it will look? So this is 3D plus 2, then 6. Okay, this is also strong field ligands. So 1 2 3 4 5 6, and this is also 5. So same things will happen. So T2G to T2G, so that will be A will be there. After that if you look this one, so here that is chromium 2 plus and that is chromium 3 plus. So this will be so this case, and this is D4, and water means that is high spin. So this is 1 1 2 3 4, and this is D3 means 1 2 3. So this is half spin, so this will transfer to here. So this is EG to EG. Okay, this is EG to EG. Now we look here, then this is Ap2 plus, this is Ap3 plus. So this is D5, so this is D6, this is D5. Okay, so electrons will be D6. So this is ammonia, so this is again weak field ligands. So 1 1 2 3 5 6. Okay, this is also weak field ligand. So 1 2 3 4 5. So transfer is from this so both are the half filled, so this is transferred to here, so that is T2G to T2G. Okay, for this case, and because from labile to inodes and this both are half filled, then we will go for T2G. If this is half filled and this is unfilled, then we will transfer to this, because now this both are half filled, so we will transfer to here. Okay, so from label to inert, so we will transfer from here to here. Okay, so that is T2G to T2G. And this case we see that cobalt. So here we see that both are low spins. Here both are low spins. Here what you see that both are high spins. Here what you see that both are high spins. Here what you see that both are low spins. But whatever you see that we have solved this one, this is one is low spin, another is high spin. Also this is T2G to EG. So rate will be E A, then we will go for T2G to T2G. This will comes, that is C. Then we have this is EAC, then this is, then we have that B, then we have the D. Okay, so this is the rate, this is the slowest, because here that spin is also changing, also the change with bond length, so both cases are changing, so this is the lowest. So always remember that, for outer sphere mechanisms, this CO NH3 2 plus CO ligands, let's say 6 2 plus and 3 plus case, if ligand is NH3 EN water and case like any we have that pyridines, whatever that pyridines, and we have that OH minus. So this is this will out, so this type of groups will be there then, because that will happen, that outer sphere inner sphere mechanism will happen if they have that pi acceptor ligand. So if this is sigma donors, or if it is pi donor and it is cobalt 6, then this will always happen, this rate will be, rate is slowest. Okay, now we will look at last concept of outer sphere mechanisms, that is outer sphere mechanisms can be two types. One is self exchange, another is cross exchange. Okay, so self exchange, where it will happen, that self exchange is like whenever we have that same metals, ApH2O 6 2 plus and ApH2O 6 3 plus, this type of same metals, then self exchange will happen. That cross exchange is like if we have that FeCN 6, let's say this is 4 minus, and if we have that molybdenum, let's say MOCN6, this is let's say 4 minus, this type of reactions, let's say this is 3 minus, then this type of case, that if that metals are different, then cross exchange reactions will happen, and this cross exchange reactions generally the faster than self exchange. Why? Because you see that here that delta G naught for this case will be so if you calculate that E naught, electrochemistry, you know that electronegativity for this case will be the 0, but for this case electronegativity will be some positive value. So if it is this value, then we know that delta G equal to minus NF E naught cell. Okay, so my if this is positive value, then this delta G is become more negative. Okay, and if it is 0, then it's going to become below 0, but for this case delta G value get negative, so this reaction is spontaneous and this reaction is fast. So generally that cross exchange reactions are fast than self exchange reactions. So generally whenever this cross exchange will happen, then that reactions are generally faster than self exchange reactions. Okay, so we already discussed about of self exchange reactions, that is by taking the same metals. Now we'll discuss about of some cross exchange reactions. So cross exchange reactions. So this type of reactions, like if we say that so we will take that different metals 2 plus and we take that Fe, this type of metals, then this different metals, so this is cross exchange reactions will happen. Okay, so you will do this reaction, then this is what, this is rubidium 2 plus and this is ferrous 2 plus. Let's say take this is 3 plus. Okay, so same as we take as self exchange reactions. So this is which type of group, iron groups. So this is D6, this is D5, and this is always low spin complexes, and here it is will be high spin complexes. So this is 1 2 3 4 5 6, and this is 2 3 4 and 5. Okay, so this is easy. So this is the reductants and this is oxidant. So electron transfer from reductant to oxidant, so this will transfer to here. So T2G to T2G will happen. Okay, so these reactions are generally faster where their cross exchange reactions will happen. Okay, so for this one famous equations is there, that is Marcos equations. That is Marcos equations. What that Marcos equations is there, that we have the two reactions like this, rubidium and this. So what happened that here also 3 plus is there, let's say this is also 2 plus reactions is happening. Then what happened that for these reactions so Marcos equations, let's say if we have that Fe to 6, 2 plus and 3 plus is there, one reactions, and other reactions, let's say rubidium NH3 6, 2 plus and 3 plus is there. Then what happened that for this one that is one rate is there, for this let's say the rate is K22. Okay, for this the rate is K11, for this rate is K22. Then that reactions of this both the rate is, let's say K12. So for what will be the K12 rate? So to calculate that K12 rate, what we say the K1 rate, suppose it is given that what is the rate of this, suppose given K11, and for this rate is, let's say K22. Then what will be the rate if we are doing that adding these two, that is K12, what is the rate? So for that rate, what is that that equation says K12 is K11 this rate into this rate, okay, into some equilibrium will have K equilibriums with some F factor, that is whole root. So this is the way to calculate the rate. This is called that Marcos equations. Marcos equation is that cross exchange reactions where two reactions is happen But if you do that cross reactions, then what will be the rate to calculate that Marcus equations as given? And this factor, this value is, if given, take that value, otherwise means not given, always taken as 1. Okay, so this value is given, this value will given, this value, all will given in questions. Then we will easily calculate that K12 reactions. Okay, so this is called that Marcus equations, and this is the K equilibrium constant. This is equilibrium constant. Okay, that will given to you. So today up to this, in the next class we will solve that previous year questions that comes from outer sphere mechanism and inner sphere mechanism. So today up to this, thank you.